Welcome back. Today we're going to talk a little bit about isotopes. So we've talked about protons and neutrons, both found in the nucleus. We talked a little bit about electrons. Protons identify the atom, right? So for carbon, for example, we can have 2 or 3 different isotopes of carbon. So an isotope means it's still carbon, so it still has 6 protons, but it has a different number of neutrons. And because it has a different number of neutrons, it has a different mass or a different mass number as well, right? So carbon-14 and carbon-12 are isotopes. There's also carbon-13. Why are they isotopes? Well, they're both carbon, so they both have 6 protons, but carbon-14 has 8 neutrons, 14 minus 6, and carbon-12 has 6 neutrons, 12 minus 6, right? Carbon-13, 13 minus 6, would have 7 neutrons. So sometimes we write in this notation for isotopes, which is pretty straightforward. We have the element symbol here, so you might want to label that for yourself. Okay. We have the mass number on the top here. That's always a whole number. And we have the atomic number down here. Okay, sometimes we leave that atomic number off. So for chlorine-37, we would have Cl, right? 37 is its mass number. We can include the 17, but we don't have to. Chlorine-35 would be like this. Carbon-14, 6 protons would be like this. Lead-208, right? Lead's atomic number is 92. If we didn't want to look that up, we could just leave it like that. Here's another slide illustrating what an isotope is, right? With potassium. Potassium has 3 isotopes, potassium-39, 40, and 41. Number of protons is the same in all of them. Number of electrons is the same in all of them. It's the number of neutrons that is different. This slide, a little bit of a recap from last time. Maybe you want to pause and fill this in. You'll need your table. Sulfur has an atomic number of 16, so 16 protons. Protons equal electrons, right? Protons are what are telling you the symbol. The number of neutrons here is also 16 because of 32 minus 16. 32 minus the number of protons. Number 6 is carbon. It also has 6 electrons. If it has 8 neutrons, 6 plus 8, mass number of 14. Number 9 is fluorine. 9 protons, 9 electrons. This isotope has 10 neutrons, 19 minus 9. Element 54, a little bit trickier. You're probably going to have to look. I even have to look on my tables. Xenon. Atomic number 54, mass, protons, 54, electrons 54, mass number of 131. So the neutrons is 131 minus 54, 77. Now, in a minute, we're going to talk about how we can calculate the atomic mass. Okay, this is the number on the table. So if you look in the carbon box on your table, the atomic mass is 12.01. And this is a weighted average of the mass of all the naturally occurring isotopes of that element. So in other words, we've said there's 3 isotopes of carbon, carbon-12, carbon-13, and carbon-14. However, the average of 12, 13, and 14, the normal average, would be 13. But we actually do a weighted average because we want to also reflect in our atomic mass what we call the percent abundance, or how much carbon-12 there is in the sample, how much carbon-13, and how much carbon-14. That way, when we look at the atomic mass of 12.01, we know that that sample contains mostly carbon-12, a little bit of carbon-13, and a little bit of carbon-14. How do scientists come up with these percent abundances? They do a technique called mass spec. And you see the results of mass spec here, which is a graph, which shows you what the abundances are of the different isotopes. We don't talk too much about mass spec here, but if it's something you're interested in, a simple Google search will give you a little more information. What we want to focus on is how is this average calculated? So let's look at 2 examples and follow this example calculation to figure that out. Here's our first problem. We have 2 isotopes, chlorine-35 and chlorine-37. Chlorine-35 has a mass of 34.97 atomic mass units, and this percent abundance. Chlorine-37, 24.3% abundance, and a mass of 36.97 U. To calculate the average, we're going to turn each percent into a decimal. You do that by moving the decimal place over 2 places to the left. Then multiply that times the atomic mass. You repeat this for each isotope. Here we have one other isotope, so we take our 24.3% abundance, turn it into a decimal, and multiply it by the mass of that isotope. Of course, you can check the average should always be between the numbers that you are averaging, and in this case, it is. This also matches the mass of chlorine on the periodic table. This mystery element. This mystery element has 2 isotopes. Same procedure, mass times percent abundance as a decimal, plus mass times percent abundance as a decimal. Gives you an average of 10.81 U. That would be the atomic mass of element X. We could ask a follow-up question. What element is element X? By taking a look at your periodic table, you can see that boron has a mass that's closest to 10.81 atomic mass units. One thing that's a little tricky is how this mass number is different from the atomic mass. Remember, the mass number is talking about just one individual atom. It's a whole number, and it's from counting the protons and the neutrons. Atomic mass is a weighted average. This is saying now we have a sample of carbon, for example. You have to either calculate this atomic mass from the period or find it on the periodic table. The mass number cannot be found on the periodic table. You can't simply round the atomic mass to assume the mass number. So the mass number must be given to you, or you must be given the protons and neutrons, and then you calculate that mass number for yourself. This is a little bit tricky, and you might want to go back to the previous video if you're having trouble with this idea of mass number.